Okay, very good evening, all. Now we are going to start our today's session by Professor Parag sir. Now I request Mr. DP Deshpande to introduce our today's guest speaker.
Thank you, sir. I welcome you all for this session of FDP. I believe that Dr. Parag Gogate sir needs no introduction, as his name is a synonymous with excellence and innovation in chemical engineering. However, as the format of our FDP, it required to introduce the guest speaker. So it's my privilege to formally introduce him. Dr. Parag Gogate sir is a renowned professor in chemical engineering at Institute of Chemical Technology, Mumbai, where he also served as controller of examination. Sir has completed PhD from ICT. Dr. Gogate sir is a leading expert in cavitation phenomenon, wastewater treatment, design multi-phase reactor, separation process, and process intensification. His extensive research contribution include over 435 publication in international journals and 30 book chapter reflecting his profound impact on field. Dr. Gogate sir is a sought after speaker, having delivered more than 100 invited talks and seminar, participated in 20 international conferences, and served as a faculty for Indian Chemical Council refresher course. His consultancy expertise spans process intensification, process improvement, and wastewater treatment, benefiting numerous industrial organizations. A a dedicated mentor and advocate for chemical engineering profession, Dr. Gogate sir has organized refresher course, seminar, and student competitions. As a long-standing member of executive committee of IICHE MRC and National Council, he has actively contributed to the professional growth. Additionally, Dr. Gogate sir is a senior vice president of UDCT Alumni Association, reflecting his commitment to community engagement. Dr. Gogate sir exceptionally academics and professional achievements makes him an invaluable contributor to this FDP, offering insights into a sustainable practices in energy and environmental sector. Let us welcome Dr. Gogate sir, whose presence today is assured to inspire and enlighten us. Thank you. Over to you, sir.
Yeah, thank you, Dr. Deshpande, and thank you, Dr. Shailesh, for giving the opportunity. I'll definitely again share the screen.
Yes, we can see the screen.
Yes. Yeah, is it visible, Shailesh?
Yes, sir, it is visible. But yes, you need to go to the full screen mode.
Full screen, yes. But
Not yet, sir.
yeah, I'll just. Is it full screen now?
Wait,
No,
sir.
sir.
No. Okay.
Sir, first you have to full screen it and then share that full screen. Because
Yes, I'll do that. Yeah. Yes. Is it okay
Perfect,
now?
sir.
Yes, it's
Yes,
there.
perfect.
But the slide is changing. Or yeah. Is it changing?
Yes,
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 sir.
it's
Yes,
changing.
yes, sure.
Fine. So I think somehow I seem to have lost touch of Google Meet now. But anyway, now everything is sorted out. Uh,
Yes.
yeah. So we are going to talk about. We are going to listen to something on improvements in industrial wastewater treatment. Of course, the objective would be to reduce the impact on the environment, because any wastewater being discharged into the environment or natural surroundings is going to give you a problem, and then that's going to damage our natural resources. So definitely not a sustainable thing, right? So we want to maximize our resources, and industrial wastewater is a major kind of factor which can affect the environment. So we will have to look into some of the modifications that are needed to kind of improve the wastewater treatment facilities in the industries. So if you look at the existing treatment schemes, usually we start with a preliminary process, that is screening of large solids. Then primary process, maybe some suspended solids are there that can be separated out. Some pH adjustment also can take place. Then we usually have a secondary process, which is mainly biological treatment, and which can have activated sludge process or filter beds. And finally, you can also think of some kind of tertiary process or a polishing stage where advanced oxidation process can be used. We can also have evaporation based, but these are going to be energy intensive operations. So even if it's a multiple effect evaporator or a agitated thin film drying, it's possible and definitely required when you want to have a zero discharge. Like, so many companies now, they are asked to do a zero discharge kind of facility, and in that case definitely we will require ME or ATFD. One of the components which is not shown here is reverse osmosis, like membrane based processes, and those are also going to be required, maybe supported by ultrafiltration as well. So this is essentially what is being followed, and depending on the chemical industry, of course, we will have some variations, like maybe ME may not be required or ATFD may not be required. Then you can have some sort of distributed treatment schemes which are going to be possible, because many a times you have a segregation in terms of high COD, high TDS kind of effluent, and another stream which is low COD, low TDS, and then the treatment process can be modified. So definitely there would be differences in terms of the overall treatment scheme, depending on what are the main products of your industry and from where the effluent is generated. What happens now is, especially when we look at new molecules being invented, some of these processes are not going to work. Or if you have a complex effluent stream, then maybe your biological oxidation may not be sufficiently working in the system, and in that you need to look at some of the modifications, and advanced oxidation processes is going to be a main factor which can improve these particular conventional treatment schemes. So we'll look into more details of advanced oxidation processes. So either these advanced oxidation processes can be used as a tertiary process, meaning I am using it for a polishing, or this can also be used as some sort of pre-treatment. So now, for example, you have a biological treatment. Now we all know that biological treatment is going to work fine when the BOD to COD ratio is say in the range of zero point 0.3, zero point 0.4, or even higher. But if I have a effluent where this BOD to COD ratio is only zero point 0.1, then definitely your biological oxidation is not going to work properly. So I can use advanced oxidation as a pre-treatment, and then change the BOD to COD ratio, bring it to a level where biological treatment is going to work fine, and then the biological oxidation can continue. It can also be used as a pre-treatment to maybe membrane operation, because membrane again is going to be a problem if I have a lot of complex chemicals present in the effluent stream. Why? Because fouling of membranes can occur. Even the membrane can get damaged, and in that case, definitely again some kind of pre-treatment is going to be useful. So we are going to essentially learn more about advanced oxidation process and how these can be integrated into either the secondary process or a tertiary polishing stage, right? So these are some more problems with biological process. Definitely you will have sludge generation, which is going to be a major factor. So if I want to dry the sludge, then I'll require some large area before that dried sludge can be sent for the solid waste management units. Definitely high energy requirement, because the moment I have a complex stream, and if I want to enhance the efficiency of biological process, then definitely I will have to give a lot of aeration, and depending on the aeration requirements, it can also mean that you are essentially spending a lot of energy. If you are talking about again MEATFD, then definitely the energy requirement is going to be very significant. If I just said something on the BOD to COD ratio, so if it is quite low, then you will have low treatment efficiency for your biological oxidation as well. And that also means that you have higher retention times. And the moment you are having higher retention times, your capital investment goes up, because essentially your volume or capacity of your biological oxidation units is going to be significantly higher. We do require technically skilled manpower, and if you maybe interact with chemical industries more and more, you will also realize that unfortunately ETP is quite a neglected zone, right? And then you don't have technically skilled manpower there, and then your performance of your oxidation units, either biological oxidation or even performance of the ME, is not up to the mark. So definitely it requires some technically skilled manpower for operation and maintenance. So we do have some problems, and that's why people are looking at some kind of modifications, and there we can think of advanced oxidation process. So advanced oxidation processes essentially would involve some production of highly oxidizing species, and hydroxyl radicals is going to be one of the major contributing species which can be generated in this advanced oxidation. The other radicals which are likely to be generated will be your sulfate radicals. If I'm using some of the chemicals like potassium persulfate, or even potassium monosulfate, PMS or KPS, we can use that as an oxidant, and then that will give you sulfate radicals. But more commonly, the oxidation processes are going to be based on hydroxyl radicals. If I look at what options are available, photocatalytic oxidation has been quite old process. So is Fenton, and so are the chemical disinfectants in terms of hydrogen peroxide as well as ozone. Now, in recent years, we have also started looking into cavitation as an advanced oxidation process. Essentially, a lot of work has been done at ICT using cavitation, and also some combinations with the photocatalytic oxidation, Fenton oxidation, or the chemical oxidants. When I'm thinking of hybrid process, essentially I am looking at increasing the rate of degradation and possible elimination of some of the drawbacks which can be there with the individual process. So for example, if I'm looking at cavitation in combination with ozone or hydrogen peroxide, we all know that ozone is a gas, and when it is introduced into wastewater, we will have a lot of mass transfer resistances coming into picture because it's going to be a gas liquid system. Hydrogen peroxide again is going to be a aqueous solution. Mostly 30% hydrogen peroxide is commonly available, and that will also give you some mass transfer resistances, though not as high as when I'm looking at ozone. Now, when I'm combining cavitation here, I'm looking at some turbulence which is going to be generated, and that will help me in terms of eliminating the mass transfer resistance. If I'm thinking of cavitation in combination with phenton chemistry, now phenton chemistry is known for high oxidation capacity, but it is also well known to create problems in terms of sludge generation, and that is mostly due to the usage of ferrous sulfate, which essentially gets converted into ferrous oxide and then ferrous hydroxide, and then it is generated as a sludge. So if I somehow reduce the dosage of FeSO4, say in combination with cavitation, then we do have some solution here for the sludge handling problem. When I look at photocatalytic oxidation, definitely I can combine it with ozone or hydrogen peroxide, or even I can combine it with cavitation. So essentially, when I look at combination of photocatalytic oxidation with ozone or hydrogen peroxide, I am essentially supplementing the process with oxidants which can give you more radicals, because UV induced dissociation of ozone or even hydrogen peroxide can occur. And we all know again, hydrogen peroxide has more oxidation potential as compared to hydrogen peroxide itself, right? So any chemicals or molecules will have lesser oxidation potential or reactivity as compared to radicals. So when I'm combining photocatalytic oxidation with ozone or hydrogen peroxide, essentially I am forming radicals, and that are going to react in a faster manner. The combination of ozone and hydrogen peroxide can also give you same effect. It's also known as a peroxon process, where again radicals are going to be generated, and that's going to be more reactive. People have tried to use different combinations, and many a times you get what is called as a synergistic effects, meaning you get more than the additive oxidation capacities, and then your treatment can be very efficient. So we'll see some of the examples as well later during this particular lecture. So if you look at outline, maybe I'm going to focus more on cavitation because that's where we do have a lot of expertise. Of course, some case studies based on work done at ICT will be presented, and then we can also have some case studies from combined processes, how effective combination is going to be helpful, and then we'll have some concluding remarks. More importantly, we can have some discussion as well. So what exactly is cavitation? So cavitation, essentially you start with a nuclei. This nuclei is going to be given some energy, where it's going to undergo an expansion phase, reach a maximum radius, and then undergo a very rapid adiabatic collapse, releasing all the energy which it has accumulated in the growth phase. The growth phase is very gradual, whereas the collapse phase is very short, and that drives a lot of chemical and physical effects inside the liquid, and these are going to be useful for your wastewater treatment. Let's look at what effects you expect. We expect highly reactive free radicals. As I said, hydroxyl radicals are definitely going to be a possibility. We do expect localized intense pressure and temperature conditions, which we call as local hotspots. And due to these local hotspots, you can also have pyrolytic dissociation of molecules. And again, radicals are going to be formed, which are going to react at high temperatures. Because you have localized intense temperature, even your reactivity is going to go up based on your classical Arrhenius equation. We do generate high intensity turbulence, and which can give you increased rates of mass transfer. And more importantly, we are looking at concentrated energy dissipation at the location of the molecular transformation. So we are looking at either the chemical transformation, or we are looking at the physical transformation as well. If you combine all these effects, we do look for an order of magnitude reduction in the energy requirement, and this is possible for any physical or chemical transformation. Now we are looking at wastewater treatment as a chemical transformation here, but remember, cavitation can be applied for a lot of physical transformations as well. For example, crystallization. So you can get better quality crystals without really affecting the quality of those particular crystals. But if I'm looking at wastewater treatment, I'm essentially looking at oxidation of these particular molecules, and then you are going to get a complete mineralization, which is maybe finally carbon dioxide and water being formed in the system. How this is possible, right? Some of you might be wondering, at one instance you are just trying to improve crystallization, whereas at other instant you are breaking down the molecules into carbon dioxide and water. Now I can give you one example even from medical field, where ultrasound is very commonly used, and many of you might have also heard about sonography, which is essentially using ultrasound, like USG. So that is based on using ultrasound. So I'm trying to see what is happening inside the body, and at that scan, I'm essentially looking that there should not be any change in the body which is going to be happening, right? So it is only a diagnostic ultrasound, we call it. It is just to see the what kind of changes are occurring inside the body. Same ultrasound has now been used to improve the drug delivery system. So I can have some patches, and ultrasound can be used to maybe just introduce some porosity where the drugs can go into the pharmaceutical drugs, of course, can go into the body, right? So for example, insulin patches people are looking at. So rather than taking injections of insulin, you can also have insulin patch. Or if you use high intensity ultrasound, focus it, it can be also used for destruction of tumors or stones which are present inside the body. And how all these is possible? It's all about engineering. I need to control the cavitation or control the application of ultrasound, and then get the desired effect. So if I'm looking at diagnostic, maybe it will be very high frequency in megahertz range, low power, and then it's used only as a diagnostic because of some attenuation. So if it is, the principle is again very simple. When you pass ultrasonic waves, if it encounters solids, if it encounters liquid, the level of attenuation is going to be different. If I'm using same ultrasound at low frequency but quite high power, then it's going to give me destruction, right? So again, same principle can be used in chemical engineering as well. I can improve crystallization, just focus on this high intensity turbulence, increase mass transfer, or I can oxidize chemicals. I'm essentially focusing on highly reactive free radicals. So control is going to be quite important here. Let's look into how cavitation is done. Simple ultrasonic bath, you will require some transducers. So I can just introduce the transducers at the bottom. I have ultrasonic bath. This is going to pass ultrasonic waves into the system. Physics will tell you that it's alternate compression rarefaction cycle. So in rarefaction cycle, I can pull the liquid molecules apart, and definitely if it exceeds the critical intermolecular distance, you can generate cavities. Again, it's a compression rarefaction cycle, so you can have different stages of cavitation, and that will give you acoustic cavitation. Hydrodynamic cavitation is also common now, looked as an alternative to acoustic cavitation. And again, it's simple Bernoulli's principle, which tells you that in a liquid flow, if I am having a constriction, I am going to generate cavities because of interchange between your pressure and velocity. So yeah, at this particular constriction, your velocity is going to go up, the local pressure can fall below the vapor pressure based on the design of this particular orifice plate, and then you are going to generate cavities which will grow based on the pressure fluctuation downstream. So I'm essentially using now the turbulence and the fluctuating pressure field due to flow changes for generating cavitation. If I want to actually do some experiments, let's say I'm at an academic institute and then I want to explore the applications of cavitation, I can start with a very simple ultrasonic horn. This is immersion type reactor. I have transducer being immersed into the reaction mixture, typically low active volume, but I'm just looking at characterization, say lab scale studies. I can move ahead, maybe an ultrasonic bath where transducers are going to be attached at the bottom. You will have liquid. This was an experiment which was tried out for formic acid. So you can see formic acid solution here. But yes, you can use any of the liquids, and then the ultrasound is going to be transferring into this particular liquid. I can have different arrangements, and typically the volume is going to be dependent on the number and the arrangement of the transducers. So you can see large cleaning tanks as well, or you can see a very simple small maybe 500 ml capacity ultrasonic bath as well. So if you visit dentist anytime, they also use ultrasonic bath, very small scale, 500 ml, 1 liter capacity, mainly for cleaning or disinfection, right? So the dental tools are just suspended in water in this particular tank, and then you irradiate it, you will get quick disinfection. And you can also visit some of the electronics manufacturing units, and they will have large cleaning tanks to clean different parts which are going to be there. So essentially what I'm trying to say, that depending on the volume, we can have a different number of transducers. I want to move ahead. Then many other times we hear in chemical industry that if I want to scale up, if it's a continuous reactor, then my the capital cost goes down because I may be operating with a lower scale of operation or lower reactor capacity. So even ultrasonic reactors can be converted into a continuous unit, and you can also have what is called as a multiple frequency multiple transducer system here. So if you look at this as a rectangular flow cell, you have transducers which are now attached at the wall, and the opposite transducers can be of different frequency. It is all to deal with again physics. I am introducing wave interference which can give me more turbulence in the system depending on how intense the collapse of cavities is going to be there. So I can have a rectangular cross section, I can even have a hexagonal cross section. Again, chemical engineering principle. So even in stirred reactors, we realize that at many places you might have dead zones, and there might be a distribution of energy dissipation in the system. So similar to that, I might have a cavitational activity distribution inside the reactor, and then I can look at different arrangements. So maybe if I'm using a hexagonal flow cell, then my distribution is going to be better. I can also think, we just talked about combining photocatalysis with ultrasound. So I can have a quartz tube here. Inside this particular quartz tube, I can introduce now a UV tube, and then it becomes simply a sonophotochemical type reactor. So you have UV radiation going from center to wall, and I have ultrasonic transducers which are present at the wall, and those irradiations are going to move from wall to center, right? So this is a combination approach which I'm already looking at. If I'm looking at hydrodynamic cavitation, essentially these will be operated as a flow system, recirculation type most of the time. So I'll have a feed tank, I'll have some pump, and then I'll have the cavitation unit here. So either it can be a high speed homogenizer or a high pressure homogenizer, and then I'm looking at recirculation back. So when it is pumped, it is passing through this particular cavitating device, it is going to be exposed to cavitation, and then it can go back into the feed tank. I can make this continuous as well, but it all depends on what level of treatment you want to achieve. If it's a significant treatment requiring quite high residence time inside this particular cavitating zone, then mostly we will operate it as a recirculation mode, because then the advantage is going to be there in terms of controlling the residence time. I can shift the homogenization by the orifice plate. So I can introduce some orifice plate here, and the geometry can change. I can also have a bypass line. Now all this piping network will allow you to control the intensity of cavitation. And even the orifice plates can be as simple as this. By the way, I can also use venturi, maybe a slit venturi or a circular venturi as a constriction. I can use this as a simple orifice plate, or I can have more number of holes, and even I can change the shape, right? Circular holes are quite easy to make, so the experimental system will be quite easy. But depending on what is the perimeter to area ratio, the shear layer is going to be affected. And then using CFD studies, people have shown that if you look at some of the complex shapes, like I want to use a triangular hole or a very small slit, then your cavitational intensity is higher as compared to a circular hole. But as I said, experimentally, it's going to be quite easy to make circular holes. So that's why most of the experimental systems will report circular holes. By the way, again, depending on this arrangement, meaning using higher number but lower diameter, or higher diameter but lower in number, essentially I am changing the perimeter. So flow area can be exactly same, but the moment I change the number of holes, my perimeter achieved is different, and then your shear layer effects are going to be different. So again, it's all to deal with your interchange between pressure drop and cavitational intensity. Pressure drop is going to be directly affecting your cost of operation, because it will essentially mean what pump capacity you will have to work with. So again, cost is going to be an important factor. I can also operate with what are called as rotating machineries, so a stator rotor type. So usually you will have a rotating cylinder with again different types of holes. You will have a stator, and then you are going to generate a lot of complex flows here. And then again, it's usually a recirculation mode, so I can have an heat exchanger in line just to control the temperature, or even this tank can be a jacketed tank as we had seen earlier, and then you are going to get the required hydrodynamic cavitation. So there are different designs which are available, and depending on what scale you want to operate, as I said, you can select any of these particular designs and then even take it to commercial scale. We need to do a lot of optimization, as I had just said earlier, that I can use the same reactors even for crystallization or for wastewater treatment, and that's going to really be an engineer's job. So I look at important design parameters now. So for ultrasonic reactors or the sonochemical reactors, I'm looking at intensity of irradiation, which is essentially power dissipation per unit area. I'm looking at frequency. So in general, if I'm looking at high frequency, low intensity, essentially I'm looking at some of the chemical effects. So I'm looking at maybe 500 kilohertz, 100 kilohertz, and associated with that related power, I can have dominant of chemical effects. But if I'm looking at lesser frequency like 20 kilohertz and lesser power, then I can focus more on the physical effects. That's where the crystallization, or say intensified natural extraction, will have low frequency, low power, even enzymatic reactions. So people have tried out ultrasound for intensifying enzymatic reaction, and essentially that will work at quite low power and low frequency. But chemical effects, wastewater treatment, maybe high frequencies are going to be better. Physical-chemical properties will not have a major control when I'm looking at wastewater, because essentially it will be water, and that's the best kind of system if I want to explore cavitation. But if I'm looking at some of the chemical reactions, then these parameters are also going to be important, like vapor pressure, viscosity, surface tension. If you have presence of dissolved gases in the system, some impurities like solid particles, then that introduces heterogeneity into the system, and then cavitation becomes easy. I can also look at operating temperature as a parameter, but again, more for your reaction. It may not be a good idea to increase the temperature when I'm looking at wastewater treatment, because essentially my discharge is going to be at ambient condition. And also, the quantities of wastewater are going to be quite significant. But if I'm looking at reaction, then operating temperature also becomes a parameter. In case of hydrodynamic cavitation, we can look at cavitation number, which is essentially the pressure drop per unit kinetic energy. And ideally, the cavitation number should be less than 1 if I want to achieve maximum benefits. In presence of gases, I can get cavitation even at higher CVs, but typical range is zero point 0.2 to about zero point 0.5 or so. And that's where cavitation works best. I can operate with higher inlet pressures, which is going to give me more intense cavitation. Maybe I can use a smaller size of orifice holes and large in number, and even the percentage free area of the orifice as low as possible, and I'm going to generate more intense cavitation. Now, one thing which you need to always remember, that it's a classical case of optimization. So for example, if I'm looking at low free area, that's going to give me a higher pressure drop. So essentially I'm increasing the cavitation intensity, but at the same time I'm also increasing the pressure drop, and my pumping energy is going to go up. So I need to balance both these, and that's where the optimization is going to be essential. Yeah, that's what the basic thing which I wanted to cover. And let's look at some of the case studies, and then we'll go into hybrid processes as well. So when we started looking into hydrodynamic cavitation, as I said, it was proposed as an alternative to ultrasound. So essentially, we thought of comparing the efficacy with ultrasound, and degradation of rhodamine B, a classical pink colored dye. So a lot of research you will see in the literature is dealing with different dyes, definitely a visible form of pollution. So, and difficult to treat using biological oxidation, because a lot of, especially the azo dyes, these are quite refractory and stable molecules. So you may not be able to degrade it using biological oxidation. Of course, people, researchers as us, try to target different things, so we can have some modifications in the microorganisms as well. But again, that's going to increase the cost. So we can look at cavitation, comparison of hydrodynamic cavitation with ultrasound. So if you can look at these plate 1, plate 2, essentially these are of different hole configurations, and these are giving much better results in terms of cavitational yield as compared to some of the right hand side where you have ACE horn, which is the classical ultrasonic horn. Nitrophenols, again, a lot of research with aromatic compounds, different substituted phenols like even chlorophenol or complex ring type structures. Again, because they are not easily biodegradable. So I can look at paranitrophenol, cavitational yield for acoustic cavitations at 7 liter capacity. It's 2.2 into 10 raised to minus 5, and you use hydrodynamic cavitation, you get higher cavitational yield. Now, why this is quantified? Because essentially this is your degradation per unit energy supply. So whatever energy I am supplying, uh, what is the benefit from that, how much quantity I am able to degrade. This is a direct quantification. So again, in literature you will find the comparison in terms of cavitational yield, cost of treatment, electrical energy efficiency. Different terms are available, but essentially it is just cost to result type analysis. If I want to compare hydrodynamic cavitation with acoustic cavitation, I'm looking at high scale of operation. Energy efficiency is going to be high. Flowability, it's not always that everything is going to be positive with hydrodynamic cavitation. We also have a problem here in terms of low cavitational intensity as compared to acoustic or ultrasound based cavitation. Solution, we can look at some of the hybrid processes which are going to supplement your oxidizing species, and let's come to the hybrid processes. So we have talked about this already, like cavitation can be combined with hydrogen peroxide. Cavitation can also be coupled with UV radiation, and this is new thing because we do have catalyst in the process. So you might have situation of catalyst inhibition. So you can get continuous cleaning of catalyst when I'm using cavitation. Definitely it's going to be a solid liquid system, so I can get enhanced mass transfer rates. I can get enhancement in the number of free radicals which are generated. I can get local hotspots, which is going to give me higher rates of chemical reactions. So a possible win-win situation, right? And a classical case where I can get some sort of synergism. I can also have a combination where I'm looking at cavitation plus UV plus hydrogen peroxide. So the moment I add hydrogen peroxide or even ozone, I am supplying it as a source of hydroxyl radicals, and that again can improve your oxidation capacity. So let's try to see whether it really works. So reactive red dye again, quite complex molecule you can see. So if I'm looking at dye degradation without H2O2, at a volume of 10 liters, I'm looking at maybe about 15-20% degradation depending on what time I'm operating. Moment I combine it with hydrogen peroxide, essentially I'm looking at 90% degradation as well. And of course, it's going to depend on how much quantity of H2O2 you are adding into the system, right? So that's where you need to optimize your hydrogen peroxide as well. But definitely, your combination is giving you much better results for this particular dye. Uh, there are a lot of studies with simulated effluent, and but again, you know that if I'm preparing the effluent, that's not the representation of a real effluent, because a real effluent usually will have a mixture of chemicals, and even the TDS and the parameters are also going to be different. So we need to explore treatment of real effluent as well, but I can understand that it's not always easy to get real effluents, and that's why in academics you will see a lot of papers with simulated effluent to start with, and then once the optimization is done, we can explore the treatment to real effluent as well. So I'm going to present one case study from real effluent as well. So we had some project going on with specialty chemicals. So it was a resin manufacturing. So we can have some alkyl phenolic effluent, equalization tank effluent, and that's why I talked in the beginning as well, that many a times you can look at distributed treatment. So I may not combine everything to equalization tank, but try to treat effluents separately depending on what is the COD level. So we did try the both the types of effluents, one at the equalization tank where the effluents are going to come from different sections, get mixed, and then essentially you are going to get a lower initial COD. And when I'm looking at only the alkyl phenolic zone, the COD levels are quite high. So you can look at about 55,000 as the initial COD. If I look at different processes, I can try out hydrodynamic cavitation, combination with H2O2, only hydrogen peroxide, combination with ozone, only ozone or phenton. And it is clear from this particular table that a hydrodynamic cavitation combined with phenton is much better and giving you about 72% of COD reduction. And definitely I'll say that SC plus penton is better, and this is even the same conclusion for your second effluent, although the percentage reduction is lower, but that is more to deal with the type of effluent and even the initial COD levels. Uh, as a general rule, usually when you have complex effluent, meaning very high CODs, your treatment efficiency is going to go down here. So if I'm looking at a COD level of maybe 1 lakh, 2 lakh, advanced oxidation absolutely may not work. That is also possible, right? So in that case, you might have to look at a different type of treatment scheme. For example, wet air oxidation is possible, right? So that can be tried out. But about 40, 50, 60,000 as the initial COD, as you can clearly see here, the treatment is possible. So if you want to propose this now and try to integrate your AOP into your overall treatment scheme, so essentially I can think of your mixing tank where the COD is about 20,000, and I want to go to a final stage where it is less than 250. So I can easily will have alum coagulation. It's a primary treatment where I'll get some partial COD reduction. Then I'll introduce AOP. Uh, where again I'll get partial COD reduction followed by biological oxidation and maybe a polishing stage, maybe carbon filtration, maybe disinfection, or AOP again, where I'll get the final COD reduction. So indeed, we try to optimize different stages, say based on using alum dosing, HC plus penton, followed by aerobic oxidation, and again final polishing stage. And here was the final result. So the sample A, even you can see a clear change in the color, not only in the color, it's also in terms of COD. So it's going from about 20,800 to less than 250. That is what is required. So definitely you can develop this particular process and get your final discharge requirements. So that's a case study or a success story with a real industrial effluent. We did try some with distillery wastewater because these are representatives finally, right? They are highly polluting, complex chemicals, so dyes, textile processing, distilleries, pharmaceutical industries, pesticides. All these are going to be quite complex chemicals to treat, and definitely many of these have significant impact on the environment as well. So we did some work on distillery wastewater and trying to improve the biodegradability index. Again, the BOD to COD ratio, as I said right at the start. So the initial COD, the ratio was around 0.14, and the moment you treat it under different conditions, you can clearly see that depending on how many number of passes, because it is operated as a recirculation mode, your number of passes essentially will mean more treatment time, and you can clearly see that it improves, but it also saturates, right? So, and this is classically expected because there would be chemicals which are going to be even refractory to hydroxyl radicals. So I can just go up to a certain level, but I'm okay with even 50 passes because that is changing it to about 0.35, and then it's your biological oxidation can continue, right? So definitely this is proven for distillery wastewater treatment. One case study from again cavitation plus phenton and imidazole is a typical pharmaceutical compound. So if I use only hydrodynamic cavitation, I get the kinetic rate constant of about 1.14 or so. The moment I combine it with H2O2, SC plus H2O2, I'm talking about 28, 40, depending on the optimum conditions. And clearly, this shows you synergism, which is more than the additive effect. So, 1 plus 1.3 maybe gives you about 2.4, but I'm looking at 40 or even 60, depending on what ratios I'm looking at. So this is definitely more than the additive effect. I can include Fenton, the rate constants still increases. I'm talking about somewhere about 244 or something. I can even think of photofenton, right? So essentially, you can think of different combinations, but it might happen that it's not always more the merrier, right? So it might happen that if I'm using HC plus photofenton, I'm looking at maybe 128 as the rate constant. But if I'm looking at only Fenton and little bit higher, sorry, hydrodynamic cavitation and higher quantity of Fenton, I'm getting rate constant of about 244. So even that eliminates photofenton, right? So I need to balance between whether I want to use photo or I just use Fenton at higher loadings, and then I'll have to, of course, deal with the sludge generation. So essentially, you need to optimize the process, and then depending on what level of treatment is required, this is the percentage degradation. So definitely the system works for imidazole as well. What combination you need to use, that definitely will have to be optimized. Another case study, so Fenton usually gives you problem related to sludge generation. So what researchers have tried out is use advanced Fenton process. So instead of adding ferrous sulfate inside this particular feed tank, I'm just using a reactor bed which is going to contain iron pieces. I can control the temperature. Uh, and while this is passing, little bit of hydrogen peroxide will be added in this particular feed tank, and while this is passing, it will interact with iron and then give you hydroxyl radicals. Because it is a iron bed, only some quantity is going to dissolve out, and then your sludge generation is going to be significantly minimized. So this was the another idea which was tried out. This was one of the older collaborations with a university in Scotland, and it was quite successful again for real effluent. And you can clearly see the TOC is getting reduced from initial, the ratio from 1 to about zero point 0.4. So essentially you're looking at about 60% treatment, and again it saturates. So maybe again the refractory chemicals are coming into picture. So I'll have to resort maybe to the biological oxidation. One, it's almost 8:30. So I'll spend maybe about 10-15 minutes on this particular process, which we worked with, again, a US based company, and then maybe we'll have some questions from your side. So, hybrid advanced oxidation reactor. So, essentially, I want to show that it's not only at lab scale, it has even moved to a practical reality, and that's the what satisfaction which a researcher is definitely going to achieve, because he or she may not be happy in terms of working only at lab level, but trying to take it to practice as well. So this was a US based company which was dealing with treatment of frack water. Frack water is usually generated in oil and gas exploration. So in any opaque countries, water is very precious, right? So we need to treat water and then try to recycle it in the process. So definitely they were looking at advanced oxidation as a possibility. So this reactor was developed as a combination of ultrasound and hydrodynamic cavitation. We had seen the plus and minus of both these types of cavitation, and definitely a combination will work better. Ozone I can again introduce as an additional oxidant, and I can also introduce electrochemistry, because again we all know electrochemical oxidation is also a lucrative process, but inhibited by mass transfer. Again, it's a solid electrode which is going to come into picture, so you will have some sort of mass transfer resistance. So if I combine everything, I can look at advantages of lower dosage of ozone. We all know, again, ozone, though it's oxidant, generation of ozone is a costly process. So if I use something in combination, I'm looking at lower dosage of ozone, which is also going to mean that it's a lower cost of treatment. If I'm combining many oxidants, I'm also looking at application to a wider range of effluent or water streams, and I'm also looking at wide effluent combinations, right? So wide range of oxidants can be generated depending on the stream compositions. If I'm looking at combinations, we have already seen this. So when I'm looking at ultrasound plus electrochemistry, I'll have increased mass transfer because of the liquid circulation which is induced by ultrasound. And I'm also looking at production of enhanced free radicals, again due to combined action of electrochemistry and cavitation. So that will give me a lot of benefits. So this is one beauty of this particular system, is it was mounted on a trailer, because oil and gas, you never know when the whales are going to go dry. So people do want to avoid capital investment at those locations, and many a times they're remote. So we want mobile solution. So this was mounted on a trailer, and then it was equipped with all the controls, and it was kind of on-site, on-demand kind of treatment. And the company later on just mounted this even on ships or uh, platforms, and then tried to treat lakes, right? Because the same concept can be, mobile concept can be applied on small ships or boats, you can say, and then these can be used to even clean up lakes. So that's again a possibility. uh, these were the general specifications. And because you have cavitation, ozone, electrochemistry, essentially you are looking at multiple reactions, and then you are generating enhanced quantity of hydroxyl radicals. Many a times chlorine is going to be present, and then you can also generate chlorine, chlorine dioxide, hypochlorous acid, you can have ferrate, you can have sulfates, because water is going to contain different salts as well. So when you subject it to electrochemistry as well as cavitation, you can generate a range of oxidants. And of course, the loading of these particular oxidants are going to be different depending on what is the salt level, or uh, if you're using ozone, it will also depend on what ozone loading you are going to use. But definitely you have a range of oxidants which are generated, and that can give you much higher treatment efficiency. We also try to do some theoretical simulations, how your cavitational activity distribution, because we want it uniform. And the general rule is that if I'm using more number of transducers, I'm essentially looking at good distribution of cavitational intensity. I'm looking at more turbulence in the system, and then I can look at even optimization of design and operating parameters. So I'm purposefully I did not have anything related to mathematics here, because I wanted to keep it as simple as possible. But yes, you can solve the equations for sound pressure field. You can use CFD COMSOL based on finite element methods. You can integrate this with radical reactions which are occurring, and some of just the pictures which are very common in any of the CFD predictions. You can have a good distribution, right? And you can even map your velocity distribution, complex profiles, but it will give you an indication that yes, a lot of acoustic streaming is happening, which is going to give you turbulence in the system. Definitely, it was tried in many hydraulic fracturing operations. The success stories were maybe over 1200 fracturing obturations were there. And clearly, you can see on the left hand side of the screen, you will find an input water. On the outside, on the right hand side, you will get a treated water. And this treated water, again, it's appearing milky, but it's not a potable water, right? So, and this milky water is mainly due to your presence of what they call as nanobubbles sometimes. But it was giving you the desired effects and was being recycled there. So that's the possibility. I can look at different sectors for this particular combination of hydrodynamic cavitation in general. I can definitely look at. Industrial wastewater like pharmaceutical industries, pesticides, dyes, textiles, wood finishing sectors. Again, wood finishing, you always use alcohol and then you have effluent which is going to contain alcohol. I can look at some options in industrial wastewater treatment. I can even look at microbial disinfection. So I'm looking at water treatment. So if you have a community groundwater supply, maybe some microorganisms are there, and then they are going to be disinfected. So I can use cavitation based process. I can even use cavitation in food processing industry, and I'm looking at some replacement to thermal pasteurization. Because if I use your conventional pasteurization, I'm looking at some loss of nutrients in the liquid foods. So there I can use food processing applications for cavitation. I can even use it in ballast water. It's a major problem in shipping industry because I want to maintain microbial diversity. So if I'm looking at cargo ships, when they're going from one place to other and they're loaded with cargo, uh, it may not happen that while coming back they will again get the same weight of cargo. So what is done is the ballast water tank are filled with water so as to maintain the balance in terms of weight. When they come back to original port, this ballast water needs to be emptied. And if I want to maintain microbial diversity, then I cannot just discharge that particular water before any kind of treatment. So I can look at hydrodynamic cavitation. And here, because of the volumes of water involved, single pass treatment is going to be the key. So, but yes, there is an application. I can look at industrial cooling water. Biofouling is a major problem, right? I can use chemical biocides, but that will give you some problems in terms of scaling. So I can use hydrodynamic cavitation and try to avoid the microbial growth, and I can also limit your scale or corrosion problem. So this is again one area. I can look at municipal wastewater treatment. People in Germany are very accustomed to use um, the municipal wastewater treatment even to generate biogas and then even to generate electricity. And if I'm looking at enhancing the biodegradability of sludge, cavitation is definitely an option. And we did have a collaboration even with a German group, and they could successfully use ultrasonic reactors to improve the biogas production. I can look at more modifications and I can go on and on. But so just one case, I'm looking at enhancing the cavitation zone. So instead of using one orifice plate, I can think of just combining it more and more orifice plates, one after the other. I'm looking at this as a complete cavitation zone, but your simple engineering will also tell you that I'm increasing the pressure drop significantly. So I need to increase the capacity of this particular centrifugal pump. But yes, I can very well think of increasing the cavitational intensity. I can even think of combining hydrodynamic cavitation with ultrasound and again operated in a recirculation mode. What is the logic? Again, to get higher cavitational intensity. So if I generate cavitation using hydrodynamic mode based on flow, it is more efficient. The cavities are generated here. These are going to pass into an ultrasonic flow cell, and then the collapse is going to occur here, and that will give me benefits in terms of more intense collapse. So easy generation based on hydrodynamic cavitation, based on more intense collapse in an ultrasonic field. So I'm combining the advantages here. So again, tried out some success story for disinfection, some success story even for biodiesel production, but not really the went ahead. Because again, when I increase the flow rate here, because if I want to produce hydrodynamic cavitation, the flow rate needs to be at a higher level. When I increase the flow rate here, the residence time in ultrasound goes down. So This was bit successful for few application, but not very successful for many of the other applications and even going to commercial scale. Now remember again, when we do research, there are some applications which may not see actual commercialization. I can give you one example even from ultrasound as well. So people did try to use ultrasound in washing machines. Idea is good because some of the dirts or some of the stains are going to be quite strongly attached to the clothes, right? And sometimes we realize that we have to even throw some of the clothes, right? Or we can try always dry cleaning, but many a times it happens that it doesn't work. So people thought about using ultrasound because if it's a targeted cavitation, your stains can be released. So if you are absorbed on the surface, those can be released. It was successful for some cycles, but then what happened is the fabric also was getting damaged, right? And then it was very difficult to control cavitation just to reach the outer surface where the stains are there or dirt particles are attached, and then the application did not go further. Membranes is another case. Membranes also, it is a possibility that I can use cavitation to avoid membrane fouling, but it can also damage the membrane surface. Enzymatic reactions, again the same thing. I can increase mass transfer, I can increase the working capacity of different enzymes or microorganisms, but I have to control the application. Maybe the enzymes should not get damaged. So essentially, it's going to be an optimization exercise. Some success stories are going to be there, some fallouts are also going to be there, just like the washing machine application, right? So it did not see the success, but researchers did try it out. Right, so that's all from my side. If I want to just conclude, and then we can have some questions as well. uh, Cavitation, it's an old phenomena. Cavitation, and in chemical engineering, cavitation is very common when we look at pumps, right? So we, of course, want to avoid cavitation. So if you go back to very basic works on cavitation, you can even go to World War days, maybe 1915, 1910, where people were studying cavitation to avoid cavitation. But over the last maybe 20 odd years, 30 odd years, people have harnessed application of ultrasound and hydrodynamic cavitation for so many fields. And there are now a good amount of success stories even at commercial level. In comparison to ultrasound and hydrodynamic cavitation, I will say that hydrodynamic cavitation is easy for wastewater treatment. Definitely, it's a possibility. I can combine it with different oxidants and then get hybrid methods where the benefits are going to be much higher. Scale up is also comparatively easier when I look at hydrodynamic cavitation, and your efficiencies can keep on rising depending on your circulating pumps, because pump is centrifugal pump is the only energy dissipating device in the entire loop. So I can easily get higher energy efficiencies at larger scales of operation. So yes, there is a lot of promise, I'll say, for these particular cavitation applications, and some success stories which I have also presented. Right, so I think that's all from my side. We can have some quick questions. We have maybe about 5-10 minutes more. Yeah, over to you.
Yes, sir. It was fantastic session. I got one question in the chat box. It was pretty much early. The question says, "What kind of treatment would you suggest for sugar factories and textile factories?"
Right. So again, sugar factories is essentially going to be a distillery. So as a pre-treatment, cavitation is going to be helpful. So the moment you use cavitation or advanced oxidation as a pre-treatment, try to improve your BOD to COD ratio, and then your biological oxidation is going to work. In terms of textile, again, advanced oxidation is going to be helpful because you can reduce your COD and then try to use say if I look at an entire package now, here I just focused on advanced oxidation. Of course, one case study was there when we looked at the entire preliminary treatment to final polishing. So distillery waste, typically people are more, or even in textile, if I want to achieve a complete solution, finally it will be with some level of your evaporators also coming into picture. The only advantage which you will get when you are using advanced oxidation is your condensate quality is also going to be better, and that can be essentially recycled back into the system. So a properly optimized process, that will depend on the class of industry. So we'll not have a universal solution, because see, all the chemicals are going to be with a different level of reactivity to even radicals or chemical oxidants. So essentially you will have to optimize this process. But as I said right in the beginning, it will have some kind of preliminary treatment, some advanced processes, and a final polishing stage, mainly in terms of some evaporation, where I'll get a solid sludge which can be disposed, and I'll get a condensate which can be recycled back into the system. Right? So it will have to be finally tailor made to the specific industry. That's what I can say at this stage.
Oh, great. Any other question, please, from participant side? The forum is open. Any question? Yes, questions? Okay, no worries. If you have any questions, you kindly reach to us. We will get you connected with the resource person or the vice versa. Okay. So now, sir, it was fantastic session. We could learn a lot many things related to cavitation, sonigation, then wastewater treatments. In one word, I would say it was related to entire wastewater treatment, which nowadays arise related to process industries. So with this, I request now Mr. DP Deshpande to propose the vote of thanks.
Okay. Thank you, sir. On behalf of Department of Chemical Engineering, DY Patil International University, and all the participants of this 1 week ATAL Faculty Development Program, it is my privilege to extend our heartfelt gratitude to Dr. Parag Gogte, sir, for delivering such an insightful and inspiring session. Dr. Gogte sir, your expertise and deep understanding of cavitation phenomenon, process intensification, and sustainable practices have truly enriched our knowledge and our perspective. Your ability to bridge the gap between academia, research, and practical application is nothing short of remarkable, and it has a left lasting impact on all of us. Your session today was not just a lecture, but a masterpiece in innovation, sustainability, and dedication to advancing chemical engineering. The practical insight, real world example, and your willingness to share your vast knowledge have undoubtedly inspired everyone here to think beyond conventional boundaries and work toward meaningful solutions for bold challenges. We deeply appreciate the time and effort you dedicated to this session. Your busy schedule. Your presence has added immense value to this FDP, and we are truly grateful for your guidance and inspiration. Once again, thank you, Dr. Parag Gogte sir, for sharing your wisdom and for being a part of this program. We look forward to future interaction and collaboration that will continue to inspire and elevate the academia and professional community. Thank you, one and all.
Thank
Yeah,
you, sir.
thanks. Yes, thank you, and it was my pleasure as well. Have a great day. Bye bye. Yeah.
Thank
Bye,
you.
sir.
Thank you.
Thank you.
One small announcement to all the participants that tomorrow we are going to start at 2 p.m. in the afternoon, and the session is going to get concluded at 8 p.m. in the evening. We'll be having three sessions of the three resource persons, followed by test and feedback, and then followed by the valedictory. So I request all the participants to adhere to the schedule and please report sharp at 2 p.m. We'll be concluding all our sessions by 8 p.m. Thank you, one and all. Thank you so much. Thank you, sir.
Okay, thanks. Bye.
Yes, yes. I request Utkar sir to kindly